In the previous lesson, we introduced a way of storing a single bit, the S-R latch. Now, if you remember, the S-R latch was set up so that what you had were two inputs, S bar and R bar. These two inputs went into a circuit that output Q and Q bar. All right, and S bar and R bar, by default, in their idle state, remember, they are active low signals. And active low signals, if they're a logic 1, they're idle. They're not affecting the circuit. When they go to a 0, that's when they go active. That's when they make changes. And so if we looked at the truth table for the S-R latch, we had S bar and R bar. We have the 4 possible combinations of 1s and 0s that S bar and R bar can take on. We have our outputs Q and Q bar, and the way that worked was if we had a 0 on S bar, we set Q. If we had a 0 on R bar, that reset Q. Q bar is always going to be the opposite. Whenever I had 2 1s going in, whatever the last value, did we come from this row or this row? Whatever the last value we put on Q was, that was going to stay on Q, and the same was true for Q bar. This top row was undefined because basically you can't set and reset at the same time. Now, the problem with this latch, and this is an S-R latch, the problem with this latch is that it's, well, kind of complicated to run, all right? It's quick. There's just 2 gates. In fact, it's the fastest way to store a single bit there is. But the problem is it's a little complicated to run. So why don't we change things around a little bit? Why don't we add a couple of additional inputs? Now, what we can do is we can have the actual data that we want to store, D. And so if I want to store a 0, I put a 0 there, I store it somehow, okay? I trigger it to be stored somehow. And what would that trigger be? Well, the trigger is what we're going to refer to as a clock. Now notice this weird little triangle thing. Looks like somebody it looks like a small bird took a bite out of this rectangle. This triangle right here identifies the clock input. And the clock is what's going to trigger the storage of D into, we still have good old Q. Q is where we're going to find what has been last stored in the box. And of course, we still have Q bar because in order to store Q, remember that circuit that we used in order to store something, we have kind of an inverter going into an inverter and that feedback loop. Well, that Q bar is still inside. Even if we don't release it from the box, it is still in the box. And so what we've got is this device here that has a data input, a clock to store it, a Q, which is what has last been stored, that's what's been stored in the box, and Q bar the opposite. And in fact, we also should be able to have access to this S bar and R bar also. Now, S bar and R bar, they're active low, and sometimes you'll see on circuitry a small circle there to indicate that these inputs are active low. The bar should be enough to indicate that in fact it is an active low signal. So, wow, that's a lot of stuff on here. That's a lot of stuff on here. Now, this circuit actually goes by 2 different names depending on this clock. It could be referred to as a D latch or a D flip-flop. All right, and they're slightly different. The end result is very much the same. We're storing in the box some data. Okay, and that data we're going to find at Q. The question is this clock. This is the guy that makes a difference here. And so there are four different types of these D latches or flip-flops that we can come up with. And I'm going to go ahead and use a slightly different terminology, but I'll show you what the terminology, how it maps to latch versus flip-flop in a minute. Now remember, what we're doing is we've got a box, right? And what's stored in the box is Q and a copy of Q represented by its inverse Q bar. Going into the box, we have data, and we also have a clock. We also have, which I'm not going to write up there just yet, because these are kind of, well, I'll talk about them in a little bit, but the S bar and the R bar, those exist on there, and they're kind of like, well, remember whenever you've learned how to program, and the very first thing you did anytime you declared a variable was to initialize it, right? Well, S bar and R bar are our ability to initialize our hardware so that whenever the hardware comes up, when memory comes up, specific special purpose memory, things that we're going to do operations in, be a really good idea to initialize them to something. And so S bar and R bar are used to initialize the hardware. Typically, it's the data D that's going to store to Q. All right. Now, how do we store to Q? I told you there were two different types, right? And these are distinguished by the clock. And I'm going to use slightly different terminology here. I'm going to use something called edge triggered versus transparent. Okay. Now, this entirely defines how the clock stores D, or how the clock triggers or causes the storing of D into Q. And let's start with this edge triggered. There are actually two types of edge triggered. There's one that's called rising edge, and then there's also falling edge. And this is all, once again, based on the clock. Now, if you remember from a very early lesson, we talked about the characteristics of a digital signal. And we talked about how if I have a 0 to 1 transition, that is referred to as a rising edge. And if we have a 1 to 0 transition, that is referred to as a falling edge. Well, those definitions map directly to these different types of edge-triggered storage devices. Specifically, what we're looking at is a rising edge-triggered latch stores D to Q the instant the clock goes from 0 to 1. All right? So at that moment, whatever's on D gets stored to Q. All right. Now, falling edge. Sounds pretty simple, right? Yeah, it is. It stores D to Q the instant the clock goes from 1 to 0. That falling edge, all right? Now, I don't know if you remember these old guys. I've got an old DSLR camera here. And inside of here, what we have is kind of a shutter, right? Something that opens to allow the light through the lens in order to be captured by the array that's going to be able to detect and create the picture, all right? We've got a button here, and whenever I push down on this button, it's going to take a picture, right? Now, the question is do I open the shutter in order to allow the picture or the image in through the lens and keep the shutter open as long as my finger's on the button, or do I do it just the moment that I push my finger down on the button? No, I do it just that moment, that instant when I push my finger down on the button. Now, the instant that my finger goes down on the button, it's going to create a rising edge or a falling edge, depending on how the electronics work in here. But basically, what we're talking about with edge triggered is it's like a camera where all you have to do is just simply push the button. You don't care how long your finger is on the button because it's the moment of change that's going to cause that capture, taking the picture of D and storing it to Q. All right. All right. Now, transparent latches. Transparent latches, they work slightly different. The way they work is that, well, just like with the edge triggered, we have two different kinds of transparent latches. We have active high and we have active low. All right. Those two different types of latches, they basically work exactly the same way, but one of them captures on a different condition than the other does. Let's go back to this camera. The very, 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 very first picture of a human being, what was it? Well, it turns out that this picture was taken on the streets of Paris. Now, back in those days, in order to get the image properly burned, you had to keep the lens open or the shutter open for a very long period of time. So, the camera was pointed down onto a street in Paris. And this street was actually filled with people. There were a lot of people on this street. But if you look at the image, you'll see that there's just one, or actually two people that are in the image. Those two people, why did they get their picture taken? Well, the reason they got their picture taken was because they were the only ones standing still. It was a man who was getting his shoes shined by a shoe shiner. So the shoe shiner moving a little bit, but for the most part stationary, and the man getting his shoes shined also stationary. They were there long enough in order to get their picture taken. So, there are conditions where you do want to have the lens open, the shutter open on this camera for a long period of time. In other words, you want to keep the shutter open as long as your finger is on the button. You've probably seen those images, a nighttime image of a city where there's the taillights of the cars are a long streak and the headlights of the cars are a long streak. Those have long periods of time that the shutter has been open. There are also really cool images where you can point the camera up at the North Star and you can see all the stars kind of spinning around it. They're not spinning, we are, but our stationary Earth, right, that looks like the stars are spinning, that also is a case where you have the shutter open for a very long time. Now, as long as the shutter's open, all that image, any changes, everything is coming straight through in order to be captured by the camera. This is true for transparent latches too. As long as the clock is at a particular level, it's basically like the shutter is open and there's a direct wire connecting D through to Q, and D is just passing straight through to Q until the shutter closes. And that means that the clock has gone to a different level. So, let's take a look at active high. What we're looking at is we're going to pass D through to Q as long as the clock equals, what is this? Active high. So as long as the clock equals 1. All right. So as long as for active high, as long as that clock is equal to 1, it's like there's a wire just simply connecting D straight through to Q. So we're going to pass D straight through to Q as long as the clock equals 1. Capture last value of D to Q when clock goes to, what is it, 0, right? All right, so just like the shutter on our camera, what we're going to do is we're going to let everything through as long as our finger is on the button. As long as the clock equals a 1, we're going to pass everything straight through. But the moment the clock goes to 0, then the last value that was stored to the last value that was on D, that's going to be captured on Q, and then D can change as much as it wants. Q is then going to stay the same until the clock goes to 1 again. And guess what? Active low. Active low says that we're going to pass D through to Q as long as the clock equals 0. Capture last value of D to Q when clock goes to 1. And there you go. There are the 4 different ways that this D memory cell can be set up. Now, which one's which? Turns out that latch and flip-flop, these map to the edge-triggered versus the transparent. Which is which? Well, it turns out that the transparent, that is the latch, okay? And you can look at it this way. Just simply passing D through to Q, but as soon as the clock goes to the other value, it latches on to the last one. Edge triggered, this guy is the flip-flop. Both memory devices, and sometimes I get a little tongue twisted and we'll call it an edge triggered latch, but basically what you're looking at is the edge triggered, which is a little bit more complicated a circuit. There's more transistors to it, so it is a little slower. That one is the flip-flop. The transparent, a little simpler. Remember that the S-R latch, that one is really the fastest memory cell we've got, just those two gates. Smaller, simpler, runs cooler. That one is the latch, okay? Now, let's go back to the S bar and the R bar. So remember, what we've got is this memory circuit. So I've got D, clock, Q, and Q bar, all right? So there are my inputs and my outputs. Now the question was, remember we had this S bar and we had the R bar. Now, the key about the S bar and the R bar is that they override, they overpower, they completely block out any inputs that are on D and the clock. So think of it this way. What I've got is this memory cell right here, and I've done some sort of a reset. Now, on the circuit board, there is a reset signal. Typically, it goes from a logic 1 whenever we're not in reset to a logic 0 whenever we're trying to reset the board. Now, that sounds like an active low signal. It is an active low signal. So what you do is you've got all these little memory cells. So think of it as like configuration cells. So these little memory circuits. The key is that I want to, whenever the processor first comes up, after it comes out of reset, I want to make sure that those guys are in an expected condition, an expected position. So what I do is, for example, let's say that I want, whenever we first power this up and whenever we come out of reset, I want this latch to be 0. I want it to contain a 0. Remember, we're initializing these just like we initialize our variables. So what I do is I make it so that the R bar is connected to the circuit board's reset signal and S bar is connected to a constant logic 1. When the system goes into reset, R bar it takes precedence over D and the clock. R bar is going to go to 0. It's going to force a 0 on Q. Let's say that another latch, another flip-flop. Let's say that we want this memory cell to be initialized to a 1 on power up. Then I would connect R bar to a logic 1 and S bar to the reset signal. Whenever I go into reset, D and the clock completely overruled by S bar and R bar. S bar becomes a 0, we put a 1 on Q, we've initialized our hardware to a known state. Okay? In the next lesson, what we're going to do is we're going to show you, based on a set of timing, how the edge-triggered and the transparent latches behave based on the inputs that we're going to be sending into D and the clock.